So again, in this next example, we have some unknown function g, and we are told that this is the series representation of g of x. So we want to find out for what values of x are these two things actually equal to one another. So again, we will use the ratio test. And according to the ratio test, r is the limit as n approaches infinity of the n plus 1 term divided by the nth term. So I'm going to have n plus 1 times x to the n plus 1 over n plus 1 is just n plus 2. And then again, I'm going to multiply by that reciprocal. All right, so if we simplify this down, on top we're going to have n plus 1 squared on the bottom, we could multiply the n plus 2 and that in. So the bottom, that's going to become n squared plus 2n. And maybe I should have highlighted this. We already dealt with those two pieces. So what's left, I have x to the n plus 1 over x to the n. So that's going to leave me with just an x on top. So we'll have another x on top there. All right, so again, because this limit is dealing with n, not x, that allows me to pull out the absolute value of x out front. So again, I have the limit as n goes to infinity of n plus 1 squared over n squared plus 2n. We're taking the absolute value of that. And so the ratio test, again, will tell us that the series will converge whenever r is less than 1. And so when I plug in infinity for n in this limit, I have an n squared on top and an n squared on bottom, so I get 1 over 1. So really what I'm getting is the absolute value of x times 1, that's r, and that's what has to be less than 1. So therefore, the absolute value of x has to be less than 1. And so to remove the absolute value, we have to include the other half of the interval, that x is less than 1, or x could be greater than negative 1, because x itself could be negative. Now, we don't know if our interval of convergence should include or exclude the values of x equals 1 and x equals negative 1. So we have to determine the endpoints and whether or not they should be included on our interval of convergence. So we have to check each of these. So let's check for when x equals 1. So when x equals 1, I would just have n x to, or 1 to the nth power is just going to be 1 over n plus 1. And so if I look at this series, as n gets bigger and bigger, like if I plug in like infinity for n, this does not go to 0. This diverges. And in fact, this diverges by the nth term test. So since this diverges, x equals 1 will not be in my interval of convergence. All right, we also have to check our other endpoint. So I have to check x equals negative 1. So if I do that, I'm going to have a negative 1 to the n on top over n plus 1. So notice here, even though this is an alternating series, as n goes to infinity, the terms of this series are going to be bouncing or oscillating back and forth between negative 1 and positive 1. So this also diverges. So we could say that this also diverges by the nth term test. So we know that our interval of convergence will not include the -1 or the 1. So we can abbreviate interval of convergence as IOC, and our interval of convergence will be all values of x between but not including -1 to 1. So when we do this, it's really important that we must check the endpoints. So this tells us that our function and our series only agree with each other for values of x between -1 and 1. In part B, we're asked to use the first two non-zero terms of the series to approximate g of 0.5 if possible. Well, this is only going to be possible if 0.5 is on our interval of convergence. But it is. 0.5 is a number between negative and +1. So we are good to go here. All right, so this will be g of 0.5. That will be equal to our series. So I'm plugging in 0.5 for x. N stays N. And we're told to approximate this using the first two non-zero terms. Now we would start with when n is 0, but when I plug in 0 for n, that is 0. I get 0 over 1. So that is not a non-zero term. So next I need to plug in a 1. So when I plug in a 1 for n, I get 0.5 to the first power, so 0.5, over 1 plus 1, which is just 2. And then for my next term, I just plugged in a 1, so my next term I would plug in a 2. I get, I get 2 times 0.5 to the second power, over 2 plus 1, so over 3. And so that's like saying 1/2 or 0.5 over 2, so 1/2 divided by 2 is 1/4. And that second term, 0.5 squared is 1/4, but times 2, 1/4 times 2 is a half. 1/2 divided by 3 is a sixth. And when I add that together, I get 5/12. So g of 0.5 is approximately 5/12 using the first two non-zero terms. All right, in part C, we're asked to use the first four non-zero terms of the series to approximate g of 1.1 if possible. However, notice that 1.1 is not on our interval of convergence. So we cannot use our series for this approximation. For 1.1, the series and the function will not agree. So we could say since 1.1 is not in the interval of convergence, or the IOC, I cannot use the series to approximate g of 1.1. All right, try this last example on page 103, and when you are ready, check the video. All right, so I will use the ratio test to find the interval of convergence. So I need my n plus 1 term. So that's 2x to the n plus 1 plus 1, so n plus 2 over n plus 1 squared divided by the nth term, so times the reciprocal. All right, so when we go to simplify that, let's see, I'm going to have a 2x left from what is on top. And then we're also going to have an n squared on top and an n plus 1 squared on bottom. So I could pull out the absolute value of 2x. All right, and then when I evaluate this limit as n goes to infinity, well, I really could think of that as n squared over n squared. So my limit becomes 1. So the absolute value of 2x times 1 is what I get. And again, I know this converges when my ratio r is less than 1. So if the absolute value of 2x has to be less than 1, I could drop my absolute value by saying 2x can be less than 1, but greater than -1. And then I could divide both sides by 2 to get x by itself. So -1/2 is less than x is less than 1/2. But I still must check my endpoints. So I'm going to check x equals -1/2 first. All right, so if I go ahead and plug that in, 2 times -1/2 is just a -1. So I get -1 to the n plus 1 power over n squared, not 2, n squared. And so when I look at this series, this is an alternating series. So if I think of it as just 1 over n squared, if I get rid of the alternating piece, 1 over n squared is a series that goes to 0 eventually, and the magnitude of our terms is decreasing. So this would converge by the alternating series test because 1 over n squared would decrease in magnitude to 0. All right, so then I also need to check my other endpoint, x equals +1/2. So when I do that, well, let's see. So 2x, so 2 times 1/2 is just 1, and 1 to the n plus 1 power is just going to be a 1. So I get 1 over n squared. And I know that this series converges by p series. Okay, so all of that to say, when I write my interval of convergence, because my endpoints, when I plug my endpoints into the series, because the series converges there, my endpoints must be included on the interval of convergence. In part B, we're asked to integrate this function for x values between 0 and 0.1, but those values are on the interval of convergence, so that's going to work. And so it wants me to use the first 2 terms of the series to approximate this. So remember, the series itself is h of x. All right, so we're going to integrate from 0 to 1/10 of h of x. And we're going to approximate h of x using the first 2 terms of the series. I have to look at my series again. All right, so when I plug in, let's see, when I plug in n equals 1, because again, I would start with n equals 1, I'm going to get 2x squared. Well, 2x squared divided by 1 squared, so 2x squared. And then when I plug in n equals 2, I'm going to get 2x in parentheses, 2x cubed, so to the 2 plus 1 power, divided by 2 squared, so divided by 4. So if I just simplify this a little bit, I really have 2x squared. 2x, that quantity cubed is 8x cubed. So this simplifies to 2x cubed when I divide that by 4. And now when we do this, oh, you know what? I made a mistake over here. Ooh, this 2x should have been in parentheses. So this should be a 4x squared. Sorry, my bad. All right, so as I just illustrated, be careful when you're plugging in values to get your terms in the series. All right, so we should have 4x squared plus 2x cubed. And when we go to integrate that, we're just using the power rule here. So I know when I integrate 4x squared, that should be 4/3 x cubed. When I integrate 2x cubed, that's going to get me 2/4 or 1/2 x to the 4th power. All right, so when I go ahead and plug in 1/10, I'm just going to do that as a fraction. So I get 1/10 cubed. So 4/4 times 1/10 cubed plus 1/2 times 1/10 to the 4th power. And then notice when I plug in 0, I would get 0. So I could subtract 0 from that. All right, so that's really like 4/3 times 10 to the 1st, 2nd, 3rd. So 1,000th plus 1/2, 1/10 to the 4th. So 1st power, 2nd power, 3rd power, 4th power. So I really have 4/3,000 plus 1/20,000. And to get common denominators here, I think my least common multiple of 3,000 and 20,000 is probably going to be 60,000. All right, so I had to do like 3,000 times 20. So that's going to be 4 times 20 is 80. And then let's see, 20,000 times 3. So 1 times 3, that becomes a plus 3. And we get 83/60,000 for our approximation.